Right, ladies, today we are starting with a new section, Geometrical Optics, and please note this is a physics section. The previous sections that we have completed were chemistry sections. So, first thing we're going to look at is the difference between reflection and refraction. These are terms that we have come across already. I'm sure you can remember last year when we were busy with sound, we actually spoke about this as well, but this year we are going to look at reflection and refraction in terms of light. So, reflection. When light strikes a surface through which it cannot pass, it bounces back into the same medium, and this should sound familiar to you because when we spoke about reflection of sound, we also described it as being an echo. So it was about waves bouncing off a surface. So same thing happens here, but it's just light that we are looking at. So if you look in your textbook on page 104 at figure 5.2, you'll see that you've got a mirror and then you've got a ray box, which I haven't drawn, which provides the ray of light or the thin beam of light that travels towards the mirror. In the first diagram, the light ray strikes the mirror at an angle of 90 degrees, so it will bounce back and move all the way back to the ray box. In the second diagram, the ray box is placed over here, so I've got a ray of light that travels towards the mirror. As you can also see here, we use arrows to represent the light rays because we need to see in which direction the light is traveling. So over here, reflection takes place, the light bounces off the surface and travels back into the medium. So just a bit of terminology that is important. The dotted line that I've drawn in here is called the normal. The ray that travels towards the surface is called the incident ray, and the ray that travels away from the surface is called the reflected ray. And then also the angle between the incident ray and the normal is called the angle of incidence, and the angle between the normal and the reflected ray is called the angle of reflection. So over here I've got all the definitions for you, and this of course comes from the guidelines. So normal, the line which is perpendicular to the plane of the surface. The angle of incidence, the angle between the normal to a reflecting surface and the incident ray. The angle of reflection, the angle between the normal to a reflecting surface and the reflected ray. And then lastly here, you also need to know about the law of reflection. When light is reflected, the angle of incidence is always equal to the angle of reflection. So if we go back to this diagram over here, the angle of incidence is equal to the angle of reflection. So those two angles there would be equal according to the law of reflection. Right, then what about refraction? So firstly, our definition from the guidelines: the change in direction of a light ray due to a change in speed when light travels from one medium into the other of different optical density. So you can see that with refraction, it's about the bending of light. That's how it's also sometimes described, because there's a change in direction. In this definition, they also talk about optical density. So of course, there's a definition for that in your guidelines as well. Optical density is a measure of the refracting power of a medium. The higher the optical density, the more the light will be refracted or slowed down as it moves through the medium. So a couple of things there. We find that light travels at different speeds through different mediums, and it will travel faster through air, for example, compared to glass, because air is optically less dense compared to glass. The maximum speed of light is 3 times 10 to the power of 8 meters per second, and that was measured in a vacuum. The symbol that we use for this is C. So c is the speed of light, and that's always 3 times 10 to the power of 8 meters per second. Then you must be able to calculate refractive index. The symbol that we use for that is a N, and the refractive index of a material is the ratio of the speed of light in a vacuum to the speed of light in a material. So if you want to determine the refractive index of a material, you need to know the speed of light through that material. So the formula that we use looks like this. N, refractive index, is equal to C, speed of light. So that is always going to be 3 times 10 to the power of 8. And V is then the speed of light through the material. So if we want to calculate, for example, the refractive index of water, we'll say that N is equal to C divided by V. C is 3 times 10 to the power of 8 meters per second always. V is the speed of light through water, so that would be the speed of light through water, which was measured at 2,25 times 10 to the power of 8 meters per second, which gives us a refractive index of 1,334 for water. And here you can also see, because it's a ratio and this unit will cancel out, the refractive index has no unit. On page 106 of your textbook, there is a table with the refractive index of different substances. Of course, you are not going to learn that, because if you need it in a question, that will definitely be supplied as part of the question. And then just over here, materials with a high refractive index will also have a high optical density, and light will travel slower through them, because the higher the optical density, the slower the speed of light. And although the speed might change, just remember the frequency actually stays the same. But we'll talk a little bit more about that later. So, just to finish off, when light travels from air into glass, what is going to happen? It's going from less dense into optically more dense. So it is going to slow down. So through glass, it will travel slower compared to air. And what actually happens is it refracts towards the normal. It bends towards the normal. So terminology, once again, this is going to be called the incident ray, and this is going to be the refracted ray, because this is refraction that takes place over here. The normal is drawn in again. That always makes an angle of 90 degrees to the surface, and the angle between the incident ray and the normal is the angle of incidence, and the angle between the normal and the refracted ray is the angle of refraction. And because it bends towards the normal, your angle of incidence is going to be greater than your angle of refraction. Now, when we look at the light traveling from glass into air, it's going from optically more dense into less dense. So it's going to speed up. So through air, it's going to go faster compared to glass. So it is going to be refracted here again, but now it bends away from the normal. So what is going to happen here? Your angle of refraction is going to be greater than your angle of incidence over there. So if we take that now and add those two scenarios together, then we end up with something that looks like this. And you'll find this in your textbook on page 107. So this shows the path of light through a glass block. So if we start over here, it's going air to glass. So it's going optically less to optically more dense. It's going to slow down in the glass. It's going to be refracted towards the normal. It travels through the glass, and then over here, refraction happens once again, because now it's going from glass to air. But now it's going from optically more dense to optically less dense. So it is going to bend away or be refracted away from the normal. So that angle is going to be greater than that angle. So again, just terminology. This is the incident ray, this is the refracted ray. And I know for the refraction here, this is actually again a refracted ray, but because it is the ray that comes out of the block, we describe it as the emergent ray. So In this diagram, I've labeled this number 1, so that's my angle of incidence. That is the angle of refraction. That's the angle of incidence again, and that is the angle of refraction. And because here it bends or is refracted towards the normal, angle 1 is greater than angle 2. And here, because it's refracted away from the normal, angle 4 is greater than angle 3. But please make note of the fact that angle 1 is going to be equal to angle 4 and 2 is going to be equal to 3. And then also, your incident ray and emergent ray will end up being parallel to each other. So please go copy this diagram down and make sure that you know how to label it. And then what you can do for me for tomorrow, please, exercise 5.1 and 5.2, very short exercises. It should take you 10 minutes max. And then please just go look at activity 5.2 and see what you can do there. And then what I'll do tomorrow, I'll give you the answers for this, and then we can discuss activity 5.2 in a little bit more detail. Right, ladies, thank you very much.